Let's look at the question, evaluate division. We are given an array of variable pairs equation and an array of real numbers value. Well, the equation at I is an array containing ai and bi, and the values at I represents the equation ai divided by bi, which is the values at I. And each ai and bi is a string that represents a single variable. And we are also given some queries, where queries at j is cj and dj, which represents the ith query. Well, you must find the answer for cj and dj, and finally, we just return the answers to all of the queries. And if a single answer cannot be determined, we just return -1.0, and we should note that the input is always valid, and we may assume that evaluating the queries will not result in division by 0, and there is no contradiction. So, in the given input, the equation list contains only two equations, AB and BC. So, the only possible values for ABC can be derived from these two equations, right? Since E is not present in any of the given equations, we cannot determine the values for A divided by E, hence it returns -1.0. And since X is not present in any of the given equations, we cannot determine the values for X divided by X, and hence it returns -1.0. As revealed by the hint, the problem can be solved with two important data structures, namely graph and union find. So first, let's check our first approach, path search in graph. First, let's look at the example given the problem description. We are given two equations, namely A divided by B is 2 and B divided by C is 3. So we could derive the following equations. B divided by A is 1/2 and C divided by B is 1/3. And A divided by C is equal to A divided by B multiplied by B divided by C, which is 2 multiplied by 3, which is 6. Each division implies the reverse of division, which is how we derive the equations. Well, by chaining up the equations, we could obtain new equations. Well, we could reformulate the equations with the graph data structure. Well, each variable can be represented as a node in the graph, and the division relationship between the two variables can be modeled as an age with the direction and weight. So the direction of age indicates the order of division, and the weight of age indicates the result of division. So with the above formulation, we can convert the initial equation into this graph. To evaluate a query, for example, here we try to find A divided by C. It is equivalent to performing two tasks on the graph. First, we try to find if there exists a path between the two entities, and the second, if so, we can calculate the cumulative products among the paths. So in the above example, we try to find A divided by C. We could find a path between them, and then with the cumulative products are 6. So as a result, we can conclude that the result of A divided by C is 2 multiplied by 3, which is 6. As one can see, we just transform this program into a path searching program in a graph. So more precisely, we can reinterpret this problem as given two nodes, we are asked to check if there exists a path between them. If so, we should return the cumulative products along the path as our result. So given the above problem statement, it seems intuitive that one could apply the backtracking algorithm, or sometimes people may call it depth first search. So essentially, we can break down the algorithm into two steps overall. The first step, we build a graph out of the list of input equations, each equation corresponding to two edges in the graph. And the second step, once the graph is built, we then evaluate the query one by one. The evaluation of the query is done via searching the path between the two given variables. So other than the above searching operation, we need to handle the other two exceptional cases. The first case, if either of the nodes does not exist in the graph, for example, the variables does not appear in any of the input equation, at that time we can assert that there's no path exist. And the second case, if the original and the destination node are the same node, for example, A divided by A, so at that time we can assume that there is existing an invisible self-loop path for each of the nodes, and the result is 1. The calculate equation function is used to evaluate a set of queries. Well, each query is in the form of Cj divided by Dj. So this function takes three inputs: equations, values, and queries. So equations input is a list of variable pairs. Well, each pair represents the equation. Ai divided by bi is the values of I. The values input of the list is a real number that's corresponding to the values of the equations. So the queries input is a list of queries in the form of Cj divided by Dj. So first, let's initialize an empty list called results to store the answers to all of the queries. And after iterating through all of the queries, we have to return the resulting list which contains the answer to all of the queries. We iterate through each query in the query's input, and for each query, we have to check if the dividend and divisor are both present in the graph. So the graph is a data structure that stores the equations and the values. If either of the dividend or divisor is not present in the graph, then we have to set the ret variable to -1.0 and add it to the result list. If the dividend and divisor are the same, then we set the ret variable to 1.0 and add it to the results list. So if neither of the above conditions are met, then we create an empty set called visit, and then we try to call backtrack evaluate function with the dividend, divisor, and 1 as the starting value of the accumulated products. So, and then we have the visited, all of them is 4 argument. And so this is the backtrack evaluate function will return a value which will then add it to the results list. For each query, we first check if either dividend or divisor node exists in the graph, which will take O of 1 time. If either of the nodes does not exist, we will return -1.0 immediately. And in another way, if the dividend and divisor are the same, in that time, we just return 1.0 immediately. Otherwise, we try to call backtrack evaluation function, which is depth first search algorithm. It takes O of n time in the worst case. Well, the n is the number of the input equations. So this function will check if there exists a path from dividend to divisor in the graph. Since there are m queries, so the overall time complexity is O of m multiplied by n. So for each query, the depth first search algorithm is called. It takes O of n time in the worst case. So it should be noted that the space complexity is O of n, as the depth first search algorithm will use a set to keep track of the visited node. This is a graph data structure. We store the relationships between the variables in the equation, and the defaultdict is a special type of dictionary that is used to store the graph. So in this case, we have 3 keys, ABC, which represent the nodes in the graph, and each key has their own defaultdict as the value, so which represents the edges between the nodes. The keys of the nested defaultdict represent the neighbor nodes, and the values represent the edge weights, which is the value of the equations. So first, we initialize an empty graph data structure by using the defaultdict class from the collection module in Python. So the defaultdict is a special type of dictionary that returns a default value for any non-existent key. So in this case, it is used to initialize an empty graph where the key represents the nodes and the values represent the edges. So the default value for any non-existent key is another defaultdict, which will be used to store the edges between the nodes. So this means that if a node does not have any edges yet, it still have a defaultdict as its value, which can be used later to add the edges, right? So this eliminates the need to check if a node already exists in a graph before we add the edges on it. So in summary, we create an empty graph data structure that can be used to store the relationship between the variables and the equations, which will be used later on evaluate the queries. The key A has a defaultdict as its value, with the key B and its value 2.0, which represents the edge between the node A and node B with a weight of 2.0. The key B has a defaultdict as its value, with the key A and C and the values 0.5 and 3.0, which represents the edge between the node B and A with the weight 0.5 and the edge between the node B and C with the weight 3.0. The key C has a defaultdict as its value, with the key B and value 1/3, which represents the edge between the node C and B with the weight of 1/3. So this graph is used in backtrack evaluate function to check if there exists a path from dividend to divisor to calculate the product of the values along the path. And we should notice that the long value is used as default value for any of the non-existent key in the nested default dicts. In the first step, we try to build a graph from the equations and add nodes and two edges into the graph. So if we want to build a graph data structure from the equations and the values, we should use the zip function to iterate through the equations and the values in pairs, where the first element of the tuple is the equation, which is a list of two strings representing the dividend and divisor, and the second element is the value of the equation. So for each iteration, we add two edges to the graph. We add an edge from the dividend to the divisor with the value of the equation. So this is done by assigning the value to the key of the divisor in the default dict of the dividend. And then we add an edge from the divisor to dividend with the reciprocal of the value of the equation. So this is done by assigning the reciprocal value to the key of the dividend in the default dict of the divisor. So in this way, the graph stores relationship between the variables and the equations, and the value of the relationship is the value of the equation. So this reciprocal of the value is also stored, which will be used later for calculate the queries. After this step, the graph data structure is fully built and ready to be used in the next step of the function to evaluate the queries. Let's analyze the time complexity because we iterate through the equations to build a graph, and each equation takes O of 1 time to process. So therefore, the step will take O of n time to process n equations in total. And about space complexity, because we build a graph out of equations, in the worst case, well, there is no overlapping among the equations, so we will have n edges and 2n nodes in the graph. So therefore, the space complexity of the graph is O of n plus 2n, which is O of 3n, which is asymptotically equal to O of n. Let's try to call a function called backtrack evaluate, so that is used to evaluate a query from the form Cj divided by Dj. Well, the Cj and Dj are the variables. So this function takes 4 parameters. The first parameter is current node. It's being visited during the depth-first search algorithm, so it represents the dividend of the query being evaluated. The second parameter is target node. That is the depth-first search algorithm try to reach, so it represents the divisor of the query being evaluated. And the third parameter is the accumulative product. It is a variable that keeps track of the product of the value of the edges along the path from the dividend to the current node. So it is initially to set to 1, and it is passed as a parameter to the function. The fourth parameter is visited. It is a set that keeps track of the nodes that have been already visited during the depth-first search algorithm. This function starts by adding the current node to the visited set, and then we're checking if the target node is a neighbor of the current node. If it is, then the function calculates the result by multiplying the current accumulative product by the value of the edge between the current node and the target node. So the result is then stored in the rate variable and then returned. If the target node is not the neighbor of the current node, this function will iterate through the neighbors of the current node. So for each neighbor, we try to call the function recursively with the neighbor as our new current node and the same target node and the accumulated products. So this function will continue this process until we find the target node or all of the nodes have been visited. If there a path exists between the current node and the target node, then we just return the product of the edge values between the current node and the target node. So we use a conditional statement here that checks if target node is a neighbor of the current node. Neighbors is a variable that holds the neighbors of current node, which is a dictionary of the variable value pairs representing the edges in the graph to check if the target node is a key in the neighbors dictionary. If the target node is a neighbor of the current node, we calculate the final result of the division by multiplying the current accumulated product by the value of the edge between the current node and the target node, and the result is then stored in the rate variable and then returned. Here is an example when the function evaluates b and e is started by calling the backtrack evaluate function with the current node b and target node e. It will then check if B has a direct edge to E, but it doesn't, so therefore it will iterate through the neighbors of B, which are A and C, and call the function recursively, where the current node is A and the target node is C. So this time the function will check if A has a direct edge to E, but it doesn't, so therefore it will iterate through the neighbors of A, which is B. But since B is already in the visited set, if neighbor is in the visited, we use continue to skip it, so we move on to the next neighbor, which is C. Let's say G is our current node and C is our target node, and we try to do backtrack for G. So G have two neighbors, A and F. Both of them is node C. So we try to do backtrack for A. A have two neighbors, which is B and D. Neither of them is our target C. And then we'll try to do backtrack recursively for B. B have two neighbors, which is C and E, and C is the target we want. So now the target node C is already in the neighbor B, so we can now check the ret variable, which is the neighbor's target, which is 3, multiplied by the accumulated product, which is 1.5 multiplied by 2, which is 3, 3 multiplied by 3, which is 9, and this ret is 9, which is not equal to negative 1.0, so now we can break the loop and return this 9 as our value of ret. If the target node is not a neighbor of the current node, that means there is no direct path from current node to the target node. It doesn't exist. So we use a for loop to iterate through the neighbors of current node. Well, for each neighbor, we call the backtrack evaluate function recursively with the neighbor as our new current node and the same target node and the same accumulated product. So we have to check if the current neighbor has already been visited. In that case, the function will continue to visit the next iteration of the loop, right? So we have to skip in the current neighbor in that case. So this will prevent the function from getting stuck in that loop or visiting the same node multiple times. We recursively call the function to check if the result is a valid result, meaning if there is a path exists from the current neighbor to the target node. So if there is a valid result is found, then the function will break up from the loop and we will return the result. If all of the neighbors have been visited and no valid result is found, then the function will return negative 1.0, which indicates that there is no path from current node to target node, and the depth-first search algorithm will continue until we reach the target node or all of the nodes have been visited.